Okay, so let's say it is the end of the fiscal year and it's time to provide the employees some feedback. What we would like to do is to provide some kind of ranking for employee A and employee B and employee C for the purpose of allocating raises. So we want to have a number one, a number two, and a number three. And you know, employee evaluation is a multifaceted process. So this is a bit of an oversimplification, but for our purposes, we are going to use this particular number, this measure, as proxy for overall employee skill level. So we're going to use the number of minutes required to complete a certain task. So let's say, for example, my daughter works at Highway 55, and one of the tasks that she has to complete when she closes the store is to clean out the uh, ice cream machine. So let's say that this is the task that we're measuring, and for each employee we have 1, 2, 3, 4, 5 observations for how many minutes we're required to finish that task. Okay, and so we would like to figure out, well, how do we go ahead and order these employees in terms of their skill level? Well, the natural thing to do, it would not be fair to take one single reading because there are all kinds of reasons why a particular day they might be slower than another. So we take 5 different measurements, okay? And the natural way to aggregate these observations is going to be an average, okay? So let's take the mean number of minutes required for each employee. Okay, we'll start there. So this is going to be average of these. Okay, and we'll just copy that over. Okay, so let's see how much this has gotten us. So we see that employee A is 44.6, B is 44.8, and employee C is 45.6. So now we can say, okay, well, all right. It appears that the fastest is employee A, followed by employee B and employee C. However, we might observe that this is not really a whole lot of difference. So, we have less than a minute here. I mean, 2/10 of a second. I mean, 2/10 of a minute here, and the difference here is only 8/10 of a minute here between these two. So we might think, well, that's not really. Is that a significant difference? Is that enough of a difference to really make this kind of ranking system just? So, how do we figure out whether these are significant, whether the difference between these averages is really significant? So, we've come across this question before, and every time we have tried to decide whether something was significantly different from something else, we had to take into consideration the not just where the distribution was centered, but what was the shape of the distribution and what was the variability, what was the variance. So let's go ahead and think about, so these differ by less than a minute, but what about within each employee? So let's think, so we can see that employee A ranged everywhere from 41 minutes to 50 minutes, and employee B ranged everywhere from 38 all the way up to 52, and employee C looks like 41 to 51. Okay, so one of the measures of dispersion was range. So let's go ahead and record the range for each employee then, which was the difference between the maximum value. So we'll do, okay, what is the max of these, and subtract the min of all these. Okay, so what do these numbers mean? So this means that the difference between the highest number of minutes and the lowest number of minutes for A was 9, for B was 14, and employee C was 10. So we see that the amount of variability in terms of time required varies a lot more within each employee than it does from employee to employee. Okay, so another measurement of dispersion that we talked about was the variance. So let's take a look at, if we're going to talk about the variability uh, within each employee, um, uh, we probably want to compare that to the amount of variability across all of the employees, right? So that's going to be variance. Now we could use standard deviation, but variance is really the same thing. It's just the square of the standard deviation. So, all right, you can look at the variance of these. Okay. Sorry. In Excel, we have to indicate that we are using the sample variance. Var.s. Okay, so we can see that we've got the variance is similar to the range. We see that employee B had the largest range and the largest variance, and employee A had the smallest range and the smallest variance. Okay, but if we look at the variance across these means, we can do, we'll call this variance within employee, and we'll call this variance across employees. Let's just take the we're going to do variance of, well, let's put it over on the right near its name. So we'll do the variance of these means. So how much variability is there in the means of each employee? And we can see that that's actually fairly small. So we have variances within the employees that have numbers like these, and we've got the variance across all of the employees. So what we would like to do is to figure out, well, how big is this variance across the employees compared to the variance within each employee. Okay, so this is precisely what we're doing when we do an analysis of variance. Okay, we are looking at how much variance is there across each of these groups. Now you say, well, that's not a group, that's an employee, but we can call it a group because these observations are grouped within an individual employee. These could just as easily be measurements like of a shift, so shift 1, shift 2, and shift 3. But the point is we have all of these observations with a certain amount of variance, and they are logically grouped within some kind of experimental unit. Now this could be a person or a shift, or it could be an organization, or some kind of grouping. So we'll call these groups even though we're actually dealing with individual people here. And what we want to do is figure out, well, is the variability across each of these groups really significantly more than the variability within these groups? Now we can kind of look at this and say, no way, there's way more variability within the groups. But what an analysis of variance allows us to do is to put this in the framework of hypothesis testing, where we can set up a null hypothesis, and we can say that the statistic is going to follow a certain distribution. Okay, so this again is another hypothesis test, and it's an extension of the t-test. So remember, we were trying to find whether there was a significant difference in the means of 2 different groups. Well, what we're doing is extending it to 3 groups now, and we're instead of using the difference of means, now we have to look at the variance of across the groups versus within the groups. Okay, so the analysis part of this. So the word analysis has lots of more general meanings, but the original definition of analysis really just means to break apart. I don't know if you knew that, but the origin of the word is to split something, split something into its components. To split up into components. So if you were to take a car engine and to pull every little piece apart and line them all up along a sheet on the ground, this is an analysis. Okay, it's a breaking apart into components. So what an analysis of variance is doing is it's saying, okay, well let's look at the variance and then let's split it apart into its different components. Okay, so we're going to split this up into its different components. And by the way, analysis of variance is often shortened to Anova. So analysis of variance. Okay, and our particular case, we're going to be looking at a one-way Anova, which just means that we're looking at a single variable. So in our particular case, we're looking at time, or average time. Okay. There are ANOVAs where you can look at two different variables, but ours is just going to be a one-way ANOVA. Okay. So as I said, we're going to concentrate on splitting apart the variance and seeing how much comes from each individual group. So how much variance comes from belonging to a particular grouping, that is, how much variance is explained by the fact that employee A is different from employee B, versus how much random noise is there within each group, within each employee. Okay, so that's what we're doing. We're partitioning the variation, and we have we're going to call the total variability SST, and this is going to be sum of squares total. That's what SST stands for. Okay, why is this sum of, why sum of squares? We'll get to that in a second, but basically we've got this full, the variation across all of those different times, and we're going to see how much of this is variation due to random error, that is, so this W stands for within. So this is going to be sum of squares within, and then how much is due to factor. Now what we mean by factor is this is the actual grouping. So this could be, employee A versus B versus C. Or in our later example, we're going to be comparing the average drive distances among 3 different golf clubs. So this could be club A versus B versus C. Okay, so whatever it is you're doing the grouping is going to have some impact on the variability. And what we want to do is to find out, well, how big is this compared to this? Okay. Okay, so the sum of squares total is going to be equal to the sum of squares across plus the sum of squares within. Now, what we're going to really want to know is, okay, the magnitude of this one versus this one. Okay, now why sum of squares? So remember that when we were calculating the variance consisted of, was calculated with this expression. We were adding up all the differences between, the difference from each observation to its mean, and then squaring it, right? And then we were dividing that by n minus 1, okay? Now, this numerator here is really all we need. Now, this n minus 1 provides us with some kind of scaling factor, some kind of way of coming up with the mean, but really this sum of squared differences is tells us what we need to know in terms of the variability. So this here is, sum of squares. And the reason is because we're adding up all of these squared differences from some observation to some mean. Okay, and we'll see in a minute that exactly how we calculate these. They are sums of squares, but the squared differences are slightly different. Okay, and I'm going to show you piece by piece how to calculate it. Okay, so we are going to figure out uh, what is the sum of squares across. So this part for the differences across each grouping, and the sum of squares within the grouping. Okay, so our goal is to find these and then to compare their magnitudes. Okay, so that's what our goal is here. Okay. We're not going to use the total sum of squares because the truth is, because we're interested in the size of this versus this. We don't really need to calculate this. We know that these are going to add up to this, but for our purposes here and to save a little bit of time, I'm just gonna calculate the sum of squares across the groups versus the sum of squares within the groups. But I'll show you what the total sum of squares refers to. Okay. There are two slides to explain this, so if you're more of a visual learner, the next one might be a little bit more helpful. What we're doing when we want to find out the total sum of squares is we're looking at every single x. Okay, so for our employees, we had employee, A, B, and C. So this is employee. Well, let's just say we have row I, which are these, and then column J. Okay, so every single one of these numbers, this one, 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 so all of these numbers, we are going to find out, well, how far are all of these numbers from the so-called grand mean? And I'll go ahead and calculate the grand mean here. So the grand mean is just the average. So we had all of these means here. If we averaged these, it would be the same as the average of all these numbers. And you can prove that, but I'm just going to go ahead and just going to show you that the average of all of these numbers is 45. Okay, and we see that employee C is actually slightly above that, and these two are slightly below that. Okay, so the grand mean, so the average of averages, and let me take it here as average of averages, okay, for each group. So now I can just do the average of these three numbers, okay, and it's the same. Okay, so the average of averages and the grand mean are the same thing, and this grand mean is denoted the mean of means again, and it's here. Okay, the mean of means. Or grand mean. Okay, so for all of those numbers then, the total sum of squares refers to all of the numbers in, row I, column J. J is the grouping, so we have C is the number of groups, so like we had 3 employees, so C would be 3 here. So we're going to be adding up all of the rows and all of the employees, and then just taking that number and its difference from the overall mean and squaring it. Okay, so we're not going to do that because we don't do anything with this value, so we're just going to skip that. But I'm going to show you how to calculate the next ones using an example that comes from your book. Okay, so your book gives you this example where we've got 3 golf clubs, and we're curious about whether the type of golf club makes a difference in terms of how far you can drive a golf ball. Okay, so we've got 3 clubs and we have 5 measurements. So we want to see, well, is there a significant difference from one club to the next? Okay, and we can see that there is some variability within the clubs. But it does appear that some clubs seem to be generally stronger than the others in terms of how far it hits. Okay, so I'm going to be using this example to demonstrate how to calculate each of the things as we come to it. Okay, so but I'm going to be using this spreadsheet here just because this makes it slightly easier to lay out. So there's these are all the different trials for Club 1 and Club 2 and Club 3. Okay, and we're going to be taking measurements piece by piece on this worksheet. Okay, all right, so total sum of squares is calculated this way. So we've got all these different groups, and this red line represents the overall mean. So we want to see, okay, so all of these dots are observations, and we want to see, well, how far are all of these individual observations from the overall mean? So we're taking each row for each group, and then finding its difference and squaring it, and then adding it all up. Okay, and this is going to be the sum of squares total. Okay, we're gonna skip that one because we don't actually use it in the Anova, so we'll just go on to the next one. Okay, so now, so that would have been the sum of squares total. We're going to take a look at how do we find out the amount of across group variations, sum of squares across. Okay, and the way we do that is we go in for each group. So now we're adding this up from 1 to C, where C is the number of groups. We're going to multiply the number of rows, the number of observations in that group, times the squared distance from the average of that group. So see, this is J refers to the group. The average of that group minus the grand mean squared. Okay, and I'll show you the visual way of understanding that difference on the next slide. Okay, so for each group, so each group is going to have its average, right? We've got this grand mean here, which is this red line. So this is the average. Let's say the grand mean was somewhere around 216 yards. And we've got this overall mean, but within each group we're going to have a mean also. And these gold lines are the individual group means. Now what we're going to do is find out, well, how far are these group means from the grand mean? Okay, so this is group 1's mean. How far is it from the grand mean? We'll square it. Okay, this is group 2 from the grand mean squared. Okay, so we're just going to find these distances and square them, multiply it by the size of each group, and then add all those up. Okay, all right, let's go ahead and do that for our golf club example. So we're finding the sum of squared across. So the first thing we need then is each of the group means, right? So we'll need a mean for each club. Okay, so we'll just do, all right, average of these. Okay, 249. Average of these, 226, and average of these. Okay, 205. All right, okay, so let's make these boldings consistent. Okay, so these are the means within each club. So, it looks like this one, Club 1, has an average a bit higher than the others, but we want to test that by making it making it more precise. Okay, so now in order to do the sum of squares across, and I'm going to go ahead and write SSA sum of squares across, we need to add up all the squared distances from these means and the grand mean. So let's figure out the grand mean. Now, as I showed you before, we could average up all of these, or we could just do the average of the group means. That's an easier way to do it. So we'll take the average of this one, and this one, and this one. Okay, so that's our grand mean. So grand mean of 227. Okay, so now we want to just add up the squared distances of these. Okay, we'll just do that all in one cell. Okay, so we're going to do, but we have to, of course, multiply it by n, which is the size of each group, and all of these are 5. So we're going to do 5 times, okay, this minus this squared, okay, plus 5 times this, 5 times this one, minus the grand mean squared, plus 5 times this mean, and I should really remember parentheses here, this mean minus the grand mean squared. Okay, so our total, our sum of squares across then is going to be 4716. We'll mark that out as a piece that we need. Okay, so we've made one step along the way to partitioning this variance. We now have sum of squares across. Okay, so now what do we need? We need to find out the within group variation. So how do we find that? So in this case now, we need to go inside of each group and find out, well, how far are each of the individual observations from the group mean? Okay, so the distance from the particular row to that group's mean, and then we square that, okay, and then we add this all up for all of the different groups. Okay, so this is adding up the rows, and then this is adding up those totals for all the groups. Okay, so let's take a visual of what this looks like. Okay, so now we don't need to have that grand mean on there anymore. That's not part of this calculation. So the within group variation, SSW, is going to be taking the distance from each particular observation to that group's mean and squaring. Okay, so this is, let's see, if we say, if we call this 1, this is group 1, observation 1, and we want to know its distance from its group mean, and then we're going to square that, and then we're going to add them all up. Okay, so we should have, as many of these expressions as there are observations. Okay, so let's go ahead and do that. That's going to take a couple of different steps, but we'll do that on our spreadsheet here. Okay, first thing, well, let me write the word mean over on this side. That'll keep things cleaner, so that I can have this column here for adding things. Okay, so I need to take the squared distance from each of these to its group mean. So I'll do that in these cells here. Okay, so this will be this minus this group mean, and I'll go ahead and hit F4 to make that an absolute reference, and we'll square that. Okay, and then because I made an absolute reference, I can just copy down like this. Okay, all right, so now I need to do these. So then I want to, so to find out the sum of squares for this particular group, so the sum of squares within for just club 1, group 1, is just going to be the sum of these squared distances. Okay, so I'm just going to add them up, make that the sum of these. Okay, now I need to do this for each group, So I'm just going to go ahead and do it real quick. So this is just going to be equal to the distance between this and it's the group mean. Make it an absolute reference and square it. Okay. So we don't need that one. Okay, and then I'm going to add all these up. So sum of squares within for group 2 is going to be the sum of these. Okay, it's 310. And so now I need to find these distances again. So this one minus the group mean, absolute reference, squared. Okay, we find that for each of those. And so the sum of squares within for group 3 or club 3 is going to be the sum of these. Okay, 376.8. Okay, so now, so that means that the total SSW, or the total sum of squares within is going to be the sum of all of these. Okay, so I'll just do sum, and then with Excel you can just select cells and hold down the control key, and that'll just put in the commas for you. Okay, so the sum of these three. All right, 1552. Okay, let me see something here. Did I select the correct cells? Let's do that again. Okay, 432 and 310 and 376. Okay, so it looks like I accidentally selected C8 twice, so I'll just take that out. Okay, all right. So now we've got our sum of squares within and our sum of squares across. Okay, so let's figure out. Okay, now what do we do now that we have partitioned the variance? We need to be able to have some kind of concept of how big is this sum of squares across compared to sum of squares within. But we can't simply take a ratio of these two. And the reason for that has to do with the different possible numbers of these things that we could have. So notice, for example, in this sum of squares within. Now we had 1, 2, 3, 4, 5. We had 5 different sum of squares because we had 5 different rows. So what if we had 1,000 rows for each? That would mean that our sum of squares is going to be enormous. And no matter how much variation we had across, if we only had 3 groups, that's only 3 sums of squares, and that's going to always be much, much smaller than our sum of squares within, because we have 1,000 sums of squares. So we need to have some way of dividing by something to make these a little bit more comparable. The natural thing to do would be to divide by, for example, in the sum of squares across, we have 3 different clubs, right? So we would divide by 3, and for the sum of squares within, we would, the natural thing would be to divide by 5. Now that's close to it, but it turns out that similar to the way that we couldn't just divide by n when we're finding a variance, we need to adjust these a little bit to make them unbiased. Okay, so rather than just dividing by these, we have to divide by something that we're going to be calling the degrees of freedom. Now, we've come across this before with the t-distribution, and degrees of freedom is one of these concepts that makes a lot of sense if you're looking at the mathematics of the estimation. But for our purposes, we just have to know that, okay, we're going to be dividing by some kind of degrees of freedom here. to adjust this sum of squares across. Okay, so rather than dividing by 3, which is the number of groups, we're going to be dividing by the number of groups minus 1. Okay, so that's our degrees of freedom. So our degrees of freedom for the sum of squares across, in our case, we've got 3 clubs, so it's 3 minus 1, which is 2. Okay, so in this case then, our degrees of freedom for the sum of squares within is not going to be the number of observations, but the complete total overall number of observations, which in our case is 15. So number of observations minus the number of groups. Okay. And so in this case then, so we have 15 observations and we have 3 groups, so we're going to have 12 degrees of freedom. Degrees of freedom. Okay. All right. So now we have a sum of squares. We have a denominator, which is our degrees of freedom, sum of squares within, and a denominator here. Okay. So now I'm going to give you another acronym. So if we take this and divide by this, we're going to have a MSA. So this is going to be mean squared across. Okay, so this is sum squares across, SSA. This is going to be mean squared across. Okay, so, and all we're going to do is take this and divide by this. And again, the reason we do this is to just make sure that they're on a reasonable scale so that we can actually compare them. Okay, and this is going to be, as you guessed it, mean square within, mean squared within, and it's going to be this divided by this. Okay. Now I put this down on a slide here to show you this, to kind of summarize it. So we see here. Okay, so we're taking our sum squared across and we're dividing it by a degrees of freedom equal to the number of groups and our clubs or employees or whatever, the number of groups minus 1. So this is a degrees of freedom, okay? And the degrees of freedom for when we're taking the sum of squares within, we're taking the total number of observations. So, you know, remember that in our case this was 15, minus the number of groups, which in our case was 3. Okay, so and this gave us our mean squared across and our mean squared within. We're not going to worry about this because, as you'll see in a minute, we don't really use this for calculating. Okay, now, so this is kind of a lot, and we've come a long way here. But now we need to figure out, okay, well, what's going to be the punchline, and how do we summarize the relationship now between this, which gives us some kind of metric of amount of variability that is from club to club, and this one gives us the amount of variability that is within each club. So in this case, we can see that this is a lot larger than this, and we can compare the two by taking a ratio. So let's do MSA divided by MSW. Okay, so we'll set that equal to this divided by this. Okay, and it gives us this number. Okay, so this gives us the approximate ratio of the variance across the clubs to the variance within the clubs. Okay, now how do we summarize this into a hypothesis test? Okay, let's go ahead and remind ourselves how we do a hypothesis test. Okay, so the first thing we have to do is come up with hypotheses. course. So step one, we need to formulate a null hypothesis. So if we're doing an ANOVA, our null hypothesis is that the mean of group 1 is equal to the mean of group 2, which is equal to the mean of group 3. And that can go on, depending on how many groups you have. But you're basically making the starting null claim that all of the group means are equal. Okay? Now, what is the opposite of that? So if we're going to form our alternative hypothesis, what's the opposite of this? Well, we can just put it in words. We just say not all are equal. Okay, so the reason why we have to put it like this is because this test won't tell us which one of these is a not equal sign. It could be, the alternative could wind up being like this, or it could be like this, or it could be that none of them are equal. Okay, so all that we are able to say when we reject this is that they're not all equal. So that's all the ANOVA gives us, but that's sometimes enough. Okay, so we've got our first step. Okay, and our second step, where you have to decide on your level of significance. Okay, and we said that without any other information, we set it at 0.05. That is our alpha. Confidence level 0.95. And our sample size, well, that was given to us. We had 3 groups, each of which contained 5. Okay. Now, what we do in 3 is we have to decide on the distribution, the sampling distribution, and the appropriate test statistic. Okay, so in this case, when you're doing an ANOVA, the distribution and the sampling statistic are both F. Okay, so remember that we had, so far for our statistics, we had Z, which followed a normal distribution, and we had T, which followed a T distribution, which was like a normal except with a different shape of tails. Now we have this new F distribution. Now, this one is a little bit different from Z or T, because remember that these went from negative to positive. Okay, they had both negative and positive. But notice that what we have in, when we were making the ratio mean squared across to mean squared within, that we had a square difference in the numerator and a square difference in the denominator, which meant that the absolute minimum that this could be was 0. Okay, so we need to have a new distribution that has only positive values. Okay, and so something that looks like this would fit. And so now with this distribution, we don't have negative and positive. There's no such thing as a two-tailed test here. We only have positive critical value, or p-value, where we're looking for, we can reject the null if we have something out here. Okay, so in the case of the ANOVA, if we have a lot of across-group variation with respect to within-group variation, then we're going to be able to reject. So for a large F, say here, we reject the null, and we can say that these are not equal, or they're not all equal. Okay, so this is what an F distribution looks like. Okay, now, so now what we have to do, so we have to, step 4 was to decide on our critical values, or in the case of the p-value method, to go ahead and calculate, what f was. And I think we're going to go ahead and do the p-value method here. So we'll see a critical value, but let's just use a p-value for ours. Okay, and then of course 5 is going to be our decision. So we're on step 4 here, and we're calculating f. Now, so we've done a lot here, and it would be nice if there was a convenient way to tabulate everything that we've done. And it turns out that there is. The Anova table gives us a very nice summary of what we have done so far. Okay, so let's take a look, and I'm just going to jog your memory about how what we've done is summarized here on this table. Okay, so remember that we're partitioning the sources of variation. So this is across groups here, and this is within groups. Okay, so let's look over here. So we calculated sum of squares across, okay, and we did that here, okay, and we calculated the sum of squares within, okay, so how much variation is there within each group, and we did that here, this orange one. And over here, they wrote down, for our reference, the degrees of freedom. So this is what we use to adjust the magnitude of these so that we can compare them. Okay, so these are really just the denominators. So we figured out our degrees of freedom over here. We said it was 2. And then our degrees of freedom for within, which wound up being 12. Okay, and so this was the number of total number of observations minus total number of groups. And so this bottom row, which is not actually part of the hypothesis test, you can see that this is just the sum of the 2 rows above it. So for example, c minus 1 plus n minus c, the c's cancel, and we're left with just n minus 1. Sum of squares across plus sum of squares within is going to be equal sum of squares total. Okay, but what we want are these two. Sum of squares across, our mean squares across, which is our sum of squares across divided by the numerator degrees of freedom here. Okay, so this is the ratio that we're really interested in. So, and this summarizes what we want to know. Okay, so across group variance versus within group variance. So this basically is going to just be the the ratio of the cross group variance versus within group variance, and it's going to follow an F statistic. It's going to follow an F distribution. Okay, so we've got our so we've done all of these, and this table provides a nice convenient way of looking at it. But let's go ahead and take a look at the F statistic that we've calculated, and then see, well, how do we go about making a decision with regard to the null hypothesis based on this. Okay, so our MSA over MSW, which was our F statistic. Okay, now we need to convert this into a p-value. We're doing the p-value method. Now remember that when we were finding the p-value for a normally distributed variable, we used norm dist and then put in our value. Okay, and then when we were using the t, we used t dist, and we had to put in our value and then our degrees of freedom. Now with this, as you can guess, it's going to be something similar. It's going to be f dot dist. Okay, so this gives you the probability given given the value that you put in there. Okay, the value of that f. Okay, so now if we take a look at this slide that shows us the way the F statistic is distributed, we see that what we're interested in is the probability under this right tail, right? So we're going to not reject under here. And we're interested in how much area is over here, right? Because under here is the probability of observing a value by chance, right? So if we have exactly the same mean squared across as mean squared within, then this should be 1, right? So anything substantially larger than 1 is going to mean we have a significant across group variability. So we want to be, we want to see how far we are here. And so this area under here will indicate, will be the probability of observing a value this extreme if the null hypothesis is true. Okay, so we want this right tail over here. So we're actually going to wind up doing 1 minus F-dist, and then we're going to put in our p-value here, or sorry, our F-statistic. So, okay, so I'm going to do 1 minus F-dist, okay, and this was the value of my F-statistic, okay. Now, I need to put in my 2 degrees of freedom. So remember that degrees of freedom 1, or the numerator degrees of freedom, was the sum squared across degrees of freedom, which was here. Okay, so it was number of groups minus 1. Denominator degrees of freedom was number of observations minus number of groups, which we calculated here. Okay, and then we always put true here. Okay, all right, so we see that if I format this as a number and then just go ahead and format it with more decimal places, you'll see. Okay, so this is going to be my p-value. Okay, so we see that it's low. So the probability, so if there was, if all of the group means were equal, the probability of observing an F this large is this. Okay, so we can safely reject the null hypothesis. Okay, so just to complete our hypothesis test here, we found the value of our F, and it wound up being 25 point something, and our conclusion was to reject. Okay, so what's our managerial decision here then? The managerial decision is that the clubs are not the same. Okay, so, okay. Now, as I said, I bring you through these exercises in calculating things by hand, so that it becomes clear where these various numbers on the Excel output come from. But as you can guess, there is a shorter way of doing this. So what I've done here on this worksheet, and I'll make this available on D2L, is I put down the clubs here, the same measurements that we had in the other one, just to make it convenient to put it into Excel's Anova. So now we're going to do the analysis of variance just using Excel's data plugin here. So we'll go to Data, Data Analysis, and way up here at the top we've got Anova single factor. Okay, so that's a one-way analysis of variance. Okay, so we'll select that. Okay, now I can click here, and I'm going to select the labels here at the top, as well as all of the observations. Click here again. Okay, and they are grouped by columns, and the labels are in the first row. Now notice, step 3 of the hypothesis testing, you're setting your alpha here, and I'm going to go ahead and set the output to be right here so that I can just look at it. Okay, and just click OK. Okay, so all of the calculations that we did were just done in one click here. But now I think that this table down here will make a lot more sense. Okay, so this So this is actually your Anova table. It provides you with this summary up here. This is not really too necessary for interpretation, but we've got our clubs here. It counted the observations, added them up, and then took the average. And we did take these average, so this is within the group average. And we took each of these over here. So 249, 226, 205. Okay, so it did those. And it found the within group variance here. Okay, now this is the table that we slowly filled out as we went along. So SS stands for sum of squares. So it tells us that the between group sum of squares was 4716, which we got over here. Okay, so sum of squares across, we called it sum of squares across or between. They're synonymous. Okay. Okay. And the sum of squares within, or the SSW, which we calculated here, was 1119. Okay. Now, they set their degrees of freedoms, 2 and 12, same as we did. And then this mean squared is just going to be sum of squares divided by degrees of freedom for here as well as here. Okay. And then finally, the F statistic is just this divided by this. Okay. So, they got an F statistic of 25.27. And if we come back here, we see that that's exactly what we had also. Okay. And our p-value was, something very small with a bunch of zeros and then a 4. And, this, if we zoom in to here, we see that's the same thing that they got there. And this F crit, this is the critical value. So we didn't compute this, but you can do this with the f.in function. We see that anything larger than 3.8 would have been significantly different. So we had a 25. So, basically we had 25 times more variance across the clubs than within the clubs. So this tells us that the club does make a difference. Now, the reason for this summary table up here at the top is to kind of do a follow-up. We now know for sure, based on this and this, that the clubs are different, but this doesn't tell us which ones. So if we see our average here, we can probably say, well, I guess we can't really tell. We know that club 1 is better than club 2, or actually we don't know. We don't know whether these two are the same and this one is significantly different, or whether this one is significantly different and these two are the same, or if all three are significantly different. What we have to do then are a set of what are called follow-on tests, which have fancy names like Tukey's, HSD, and there's a bunch of other ones, but for our purposes here, we've been able to conclude that they aren't all the same, and that's what the Anova gives us. Okay. Okay. So this is just a reminder that the way we went about finding the p-value for this is to do f.dist, or 1 minus f.dist, and then we had our, whatever our calculated F statistic was, and then we had our numerator degrees of freedom and our denominator degrees of freedom. Okay. Now, one thing to note about this table, something that I've done in the past is I have given a table that was only partially filled in, and then the question was to finish filling in this table. And you can do that now knowing what you know, because if, for example, you had this and this, you know that this is just going to be the sum of these. And if you have you know that this cell is just this divided by this, and this cell is just this divided by this, and then you know that this cell here on the right is just this divided by this. So basically, with this, and this, so if I give you these 4 cells, you can fill in the entire rest of the table. Okay. All right, so I hope that helps. That's all about the Anova, and we're going to get into another hypothesis test next time about the chi-square statistic.